There's quite a lot of people in the society interested in solar work and auroras, noctilucent clouds, a lot of astrophotography. Phil's just sent a gorgeous photograph he did last night just to prove it was clear here. So there's quite a variety of things happening around the society here. It's quite good. It would just be really, really nice if we could all get back together again at the observatory and actually speak to one another face to face would be good, but not yet, it seems.
Yeah, no.
Yeah.
It does make a difference when you're actually in the same room as other people, I think.
Yeah, what we miss most is our tea break, where we could chat and exchange ideas, and there was always somebody to answer the questions that you had, you know, picked up during the week and things. It was just really good, but it's very difficult doing that on this setup. You know, it's good and it's been great, but that social bit is a big miss. Have you always been interested in solar physics?
Not always. I think I only really became interested in it in my last year, my 5th year.
Okay.
Up until my 4th year, I was aiming for the gravitational wave side of things. Oh. So I did an internship with the Institute of Gravitational Wave people, and I really enjoyed it. And it was Lindsay Fletcher. You'll maybe know, yeah. It was, I did a project with her my last year, and just I completely changed my mind for what I was aiming for. So yeah.
So you're looking to stay in the field?
I think so. Yeah.
You're going to stick with it. Yeah.
Quite good. Yeah. I still find it really interesting, and I think that's one of my biggest criteria. Is like just as long as I've got that motivation to keep going with it. So yeah, it's really cool. But a lot of astronomy I just think's so amazing and interesting. I think it's so easy to get drawn into it in a lot of different ways.
Certainly is. It's got a huge addictive quality to it, I've discovered. How are we doing, Dave? Is everybody in, do you think?
Yeah, I'm just chatting to Colin Steele on YouTube. So yeah, I think we're I thought there'd be more people joining on Zoom. Oh, wait a minute. I got one of our new members. Are you still there, June? You've gone very quiet. Yes, I am. It suddenly went quiet.
No, I am here. Well, we can just, can I say hello to Jane?
Hello, Jane.
Hi, Jane.
Good for you to join us. Should we just kick off then, David? Is that okay?
Yeah, fire away.
Okay. Well, let me welcome everybody, and new people as well as I was going to say old faces, but I always get around for that, who are sort of out there in Zoom land and YouTube land. We really had hoped that we would have been able to meet at the Mills tonight, even in restricted numbers, just to start getting things back to normal. But unfortunately, Storm Arwen, which was way back in November, has caused all these trees down, and it's going to take a while to get it cleared. I'm told Dundee Council have got contractors in now, and they are starting Monday, although I don't fancy their chances in this wind, to clear the fallen trees in Templeton Woods, and then moving on to Balgay Hill. So it's a bit of a neat thing as to whether this will be done to let us up on the 11th of February. But as always, David will keep everybody informed of what's happening and whether the road's open by then and we can get back up. But moving on to tonight's meeting, I am delighted to be able to welcome our speaker for tonight, which is Kristopher Cooper from the University of Glasgow. Kristopher tells me that he's almost towards the end of his PhD, only got about 6 months to go, and has been working since his first love of astronomy in solar physics, and is still really fond of the subject. So tonight he is going to tell us about His work investigating the, well, very explosive and high energy world of solar flares. And so we will hand over to Kristopher to start our talk for tonight.
Thanks very much there, and thanks very much for having me along. I've been looking forward to this for quite
Delighted.
a while. So it's a shame that obviously can't actually be up there, but it's at least good that we can still do this over Zoom. But yeah, so I'm Kristopher Cooper from the University of Glasgow, and I'm going to talk about X-raying the sun. Mainly, we're going to look at the most explosive events, I would argue some of the most interesting events on the sun. So I'll sort of just start this off by just looking at the questions that I've tried to structure this talk roundabout to have some sort of aim with it. So one of the reasons is what are the different ways that we can actually observe the sun? Something that interested me and that I didn't really know much about when I started my PhD was actually the number of different instruments that you can use and you have to use when you're observing the sun at these high energies compared to like ground, if you're doing some observations on the ground. The sun, how the sun's atmosphere is actually structured. I don't know the experience of people with or everybody when they've been observed, but the sun's atmosphere has different layers to it, just like the Earth's atmosphere. Why we actually bother looking at the high energy range? The electromagnetic spectrum is quite wide and varied. What makes this high energy stuff so interesting? And what do we actually know about solar flares and why, just to actually pick a topic and really dive into it. So yeah, why actually observe the sun in the first place? I think I've just sort of put in some general reasons why you would want to, but again, some might not be as obvious. They weren't as obvious to me, particularly the first two, where it's one of the best environments to study plasmas. Plasma physics has a wide range of applications. You know, in medicines and engineering, there's tons of applications, and the sun is one of the few environments that we can actually see with, you know, if we just build better and better telescopes, we can see how plasma interacts in a very unique environment. And that leads us on to, it allows us to test the extremes of physics. That's something that I've always been interested in myself. You know, astronomy is, you're looking at the most extreme things in the universe, and I don't know how you can't get interested in that. The third one there, space weather. Some of you might already be aware that space weather is becoming more of like a buzzword and more of a not more of a threat, but people are being made more aware that it's a threat. And that's what this diagram in the right sort of showing is that how the sun actually, how the sun-earth interaction can affect us on the ground, you know, with communications. The sun's activity puts a lot of pressure on the national grid. And I think that the last estimate that I saw is billions per year. It just putting extra strain on the grid, and all these parts having to get replaced. So it's really good to sort of understand what's happening there so you can maybe protect against that. And the last one there I've put in, I think it's probably one of the most important. It needs to be fun. Like, you need to actually be motivated and get up, you know, every day, or you actually want to go out and observe the sun. There's loads of cool things that happen. I don't think that can be understated. So going into a little bit of like how we observe the sun, and I'm mainly going to focus on the high energy stuff, but I said that there's particular things that we need to take into consideration when we're looking at the high energy stuff. And this diagram here sort of explains the first problem that you might encounter, or if you've ever just wondered why have we got some telescopes on the ground and then some have to be up in space. And this diagram shows, I don't know, can you see my mouse on the screen? Is that, if I move that? Yeah. So you'll see that any wavelength that we really see in the optical window of the electromagnetic spectrum, as you might expect, a lot of that reaches it to the ground. The atmosphere doesn't really get into the road of it. So we can have all of these telescopes, ground-based telescopes that, you know, you can have replaced technology that you can replace it and update it as you go. So that's great. And we've also got the window over here in the radio where we can have ground-based detectors. but you'll see that all the other wavelengths, they're sort of, none of them really make it to the ground that well. And so probably the next best wavelength that you could observe still sort of being at the Earth is the infrared, and there's a plane there, so that is where jets fly, but you've also got some infrared telescopes that they put onto jets and they fly up into the atmosphere so that you can get these really crisp infrared images. I think one of them's called Sophia, a very popular one's called Sophia, if you want to have a look at that. But other than that, if you want to look at any of these other wavelengths, you need to be up in space. So otherwise the atmosphere just cuts it out straight away. There's too much, the atmosphere is quite opaque. So these wavelengths don't really get down. And so that's why there's an infrared telescope there, and then anything X-ray, you can't do this from the ground. So that's why we need something up there. So there, I said, I don't know how many people were there with the chat at the start, but I did mention that there are tons of different ways that we can observe the sun, and especially in the higher energy stuff, you need to observe the sun differently. But I thought I'll just take you through a couple of the common ways that we observe the sun in like EUV. So the EUV is the extreme ultraviolet, and that moves its way into the X-ray stuff. So this is probably a very familiar setup to most of you. It's just pretty much how your DSLR camera will work, where you've got a pixel grid like a CCD chip in there that will take an image. And I've always thought that this diagram is quite a good one to sort of explain what's happening here. Every pixel is effectively just a bucket. You open the shutter, it'll take in as much light as it can in that time, and then you'll shut it and you'll read it off. And so you'll get an image that's, well, fairly pixelated. You'll get good resolution from it, and that's a very common way to take any sort of measurement on the sun. But there are other ways. There's spectroscopy. You can only get so much from an image, and so you can get a lot of dynamic information from any events that are happening on the sun. You can follow things through, physically. But spectroscopy offers us another window, and so pretty much all you're doing is just in some way, again, a lot of you might be familiar, probably will be familiar with this, you're just splitting up the light that you're getting in from the sun in some sort of way. So you can either do it with a prism or diffraction grating, something like that, and you produce a rainbow, a spectrum. And the important thing about spectroscopy is, although here this instrument, I can't remember what instrument in particular produced this image, but effectively you'll see all the absorption lines, and you can tell a lot from what you've observed from the absorption lines, depending on how wide they are. And it's the same with emission lines, with how bright they are, just the opposite side of things. You can start to tell things like what elements are there is like the really common first thing that you might think about, but you can also tell how much of each element's there, the temperature of the emitting plasma, the stuff that you're actually looking at, and from those numbers you can then go and calculate a lot of other things. You can tell how quickly things are moving as well, just by these lines. So that's something that that you might be able to match up with the image that you would have got in the pixelated detector beforehand, and you can match up to see how quickly that material is actually moving to and from the observer as well. So there's a lot of information in spectroscopy, and so there's a lot of instruments, there's a lot of active research that uses that. So those are two really common types of detector. But like I said, when you're we use them in the UV and heading towards X-ray observations. But when it gets to X-rays in particular, or even higher energies or shorter wavelengths, you need to start using detectors that might not necessarily be as familiar to people who would think of a telescope. So the first one that I'll point out is this one in the bottom left. This is, I've said it's GOES-like. Now GOES, I don't know if some of you might have heard of that before. It's pretty much a weather satellite that NASA controls, but it also monitors the sun. It monitors the sun as it monitors the sun as if it's a star, so you get no spatial information from it. It's just sort of a detector that's pointing towards the sun, and it's just collecting information all the time. It doesn't really care about the location on the sun though. And the way it sort of works is it's more like a gas chamber that you've got. So you've got this ionization chamber, and photons, X-ray photons will come in, interact with that gas chamber, it will cause a charge, and you measure the charge, and you can see how active the sun is. So if there's an event that's happened, then you'll get a spike in the GOES light curve. And this is the instrument, NuStar is the instrument that I usually use, or I've mainly used throughout my PhD, but this is a different type of instrument. So when you get to X-rays are a pain pretty much to focus. That's a big issue that you get with them. It's difficult to stop them, to actually detect them, to detect the photons, but then it's also really difficult to actually bend the photons into some sort of like image or specific location. They really don't want to bend. So what NuStar does is it has these concentric cylinders that are effectively mirrors all the way around in it. That's different shaped mirrors. So you can see that there's sort of two types of cylinders there, and they've got a slightly different curve to them each. But effectively, each shell is just separated by a tiny amount, and when a photon comes in, the mirrors internally bounce off, and then they'll focus it on a detector that's maybe about 10 meters back. So even though that you've got this equipment, this lens out in front, you still need at least 10 meters for like your focal length to actually focus anything that you've got. And as well with NuStar, not all energies can be focused the same amount. So at the higher energies, it gets harder to then focus them, and that introduces a whole lot of different issues that you might have when working with that data. When it gets to the back into the detector, you have something like this, which isn't unlike the ionization chamber in GOES, apart from it's in NuStar, it's cadmium zinc telluride. So it's a crystal detector, and effectively it's the same principle, though these photons are hitting there, you're causing a charge pretty much across that crystal, and you can then measure it. And NuStar's just got a grid of these, so you can actually get, where's it actually hit on the detector. These types of detectors are fantastic because you not only get the position of where it's hit, but you also get the energy of the photon, as well as the time that that actually hit. And so from that, you just get a list of counts of detections, but you can then build up an image later on. The bottom one, RESE, I don't know if some people will have heard of that detector. It's a similar setup at the back for, I think that's cadmium zinc, cadmium telluride detector at the back, or germanium, sorry, there's some germanium ones, I think that there's other types of detectors there, but that uses a different technique. It doesn't bother trying to focus them at all, the X-rays at all. It uses rotating collimators. So if you're familiar with a Moray pattern that you would maybe see if you try to take a picture of your monitor, and so you've got like the CCD in your phone and the pixelated grid on your monitor, you'll start to get Moray patterns, and effectively you can see that there's a grid at the back or close to the detectors, a grid at the front, and these spin with respect to each other. And so what will happen is, as you'll get some sort of like, it'll start blocking out the light and it'll let light through, and you know exactly what these grids are doing. So it means that through some sort of really weird magic maths, you can then build the image of what you've actually seen just by seeing how the light was blocked out and lit through. It's really weird, but that's another way that you don't need to focus these X-rays, and it's just to get around that issue that doing that's difficult. So yeah, that takes me on there to what we actually measure when we're looking at the sun. So I've mentioned a lot about, you'll get a photon or a particle released from the sun or emitted from the sun. It'll go through your instrument, detect it somehow, and this is the same on the ground, and then you'll get your data at the other side. And this is the same even if you're out doing observations by yourself. But what is it that you actually have on the other side? So this is probably one of the most complicated examples. This is from NuStar. It's just a big, pretty much grid of numbers. But effectively, the point in this is that when a photon hits, you're not measuring, the thing that you're recording isn't the photon, you're recording a voltage. You're recording something else as like a proxy. And so the detector's pretty much this box that's taking in this photon and it's giving you a different signal. And sometimes so it's coming in at the side here, and then the signal gets put out at the bottom, and that's really what you've got. In some instruments, that might be quite simple to look at what, you've got, what numbers you have on the screen, and put that back into exactly how many photons have hit your detector. And other things, that's really difficult. And you can see here that if I just choose one row, so if you can imagine one energy or one wavelength, that's one of these rows. And everywhere that it lights up along that one row, it contributes to what you get out at the other side. So it's sort of like there's a lot of pixels here that are lighting up just with one photon. So you might get multiple numbers out at the end from just one photon. So it's really difficult to piece all that back together at the end. So that's just a little bit about the types of instruments that we're actually measuring and what we get out at the end. And it might allude to some of the complications that we actually have at the other end, even just never mind trying to get nice results out at the end, but just trying to work with the data. But I mentioned earlier that the sun as well has an atmospheric structure. And it's, or at least that we've decided that we've broken it down like this. So I've managed to make up this figure on the right, where the lower part of the atmosphere is we call the photosphere. That's what you would see with your eye, and the more optical range. And on this graph, it's sort of going backwards, this graph, so it's from right to left. So this is a photosphere here. And then we start going up the layers this way, and it's about 6 million degrees. So that's usually a number that's a lot of people know that's maybe observing the sun. It's about 6,000 degrees. As we start going up the layers though, into what we call the chromosphere, that spans a big temperature range. But what is maybe curious is that the temperatures are going up, which is exactly the opposite of what you would think would happen. As you sort of get higher, you're filling a larger area, the temperature should start to decrease. So that's quite weird that the temperature in the chromosphere is going up. And then as you get up higher into the corona, up here, we suddenly jump up to 1 million degrees. So there's something really weird going on. It's called the coronal heating problem. That is a very big active area of research. In fact, a lot of solar research is pinned on trying to pin down exactly why this is happening. So that's really weird. The reason why I've sort of chosen this diagram though for this talk, even though that there's a lot of stuff on it, I would ignore the dotted line. And you can see the temperature in the solid black line. But the reason why I've picked it is because you might get these types of filters. So these sort of horizontal lines here indicate where specific emission lines are getting produced. And you might be able to buy filters for your camera if you're doing any solar observation about, for an H alpha, for example. I know they're very expensive, but you can get one for your own telescope to take observations on the ground. And this shows you roughly where that line is produced. So if you buy one of those filters, that's the sort of area in the atmosphere that you're going to be looking at. And you can see there's different structures as you step up. So we've got some sunspots there, and then it's still the brightest, but in the chromosphere at these points, but it's a different sort of structure. And then when you go up to the corona, you're starting to see these big magnetic loops that are up there as well. So we can sort of step up through the atmosphere in that way. So I've talked about the why or how we would actually be able to observe this higher energy emission stuff, or how difficult it is, but why is it important? Why do we want to look at that in the first place? So when you get a lot of energetic events, it's maybe not a surprise that it's going to be heating stuff up to really, really high temperatures. So that would maybe give you an idea that we're going to be looking at the higher energy stuff from the start. When it comes to UV or the extreme ultraviolet, you can observe a wide range of temperatures quite easily. You can use these pixelated detectors, and you get amazing resolution. The in the EUV range, you get a lot of useful, very distinct emission lines. You get some areas where some emission lines are on top of each other and it's difficult to distinguish them. But having a lot of these distinct emission lines, either from different elements, but you can also have ones from the same element but in different ionization states. And all of that can help you pin down the temperature quite well if you can get that information out of your observation. Because of the amazing resolution that you get, you can then, and because you can also step up through the solar atmosphere, you can track some features, what they're doing, you know, as they're going up. These are like millions of meters that you're crossing as you're going up through this atmosphere. So even though on the image it might not look like much, you're covering a massive distance to actually see what the material is doing. To give you an idea about the just amazing resolution, this image on the right is taken from an instrument called the Atmospheric Imaging Assembly. And you can see all the really fine detail in those yellows and oranges. That's from that Atmospheric Imaging Assembly that's looking in the extreme ultraviolet. The greens and the blues are from X-ray instruments. So you can see that, especially in the blue region, you'll see that that's just a big blob. It tells you where most of the hottest stuff's coming from, but you don't really get any spatial information out of that. You get a lot from the EUV, but it's difficult to get temperature and energy information at the high end. So when you're building a detector that will see all of these emission lines really well and be able to focus them, obviously I've already covered that when you get to X-rays and you know and higher, it's murder to actually focus them. You need specialized optics to do this, and so you don't really have the capability to do that with the EUV. So why are X-rays important then? What else can we get out of X-rays, and why bother taking that extra step up? Well, there's a few questions here that, as I said, that the coronal heating is a problem. You know, the corona is hotter than the surface. So if flares are potentially a candidate for what's going on here, we want to know certain things about flares. So where does it actually release its energy? Which isn't always the same as where the brightest is in EUV either. It could just mean that there's loads of material there emitting. It's maybe not even the hottest part. It's just that there's tons of stuff there emitting. How much energy does a flare actually release? How long do flares release energy for, and where does this energy go? Well, when we look at X-rays, the very first one solved by X-ray images. I said that you don't really get great resolution, but sometimes you don't need great resolution. You just need to, in comparison to UV images, you can see what part of the structure is actually hot. Where should you be focusing your attention here? How much energy does a flare release? X-ray spectra, the X-ray emission is really, really well understood. So when we get observations in X-rays and we've got a spectrum, we can pretty confidently put temperatures on that and find out how much stuff's actually there. How long does a flare actually release energy for? Because X-rays, there's always X-rays being produced, but when a flare goes, it's really obvious in X-rays. So you can actually get, you know, a more nuanced view of the flare. And so an X-ray light curve, just a time profile, will show you exactly how long that's lasted for. And where does the energy go? Again, just X-ray images and spectra. You can learn all of this just from X-rays. So X-rays in X-ray spectroscopy is essential, really, when you're looking at these high energy events. So I said that it's well understood, and I just wanted to put this in because it's sort of like, as far as you know, like the physics and the modeling and all that side of things, this is incredibly, I think, an incredibly sort of simple setup, where on the left-hand side, what I've got is just a proton. It could be an ion, just something with a positive charge, and you'll have an electron here. And an electron, through whatever reason, it might have been accelerated in a flare, effectively the explosion of the flare. It could just be really hot and whizzing about. And if what it'll do is it'll pass a proton or an ion, and it'll bend in towards, there'll be an attraction there. And so the electron will be decelerated as it sort of like bends round. Just, I mean, as an analogy, I always think about it, if any of you are as bad at golf as I am, if you're trying to do a pot and then you actually hit the edge of the hole, you'll know that the ball won't go in, but it'll swing round, and it'll sort of, you'll see a lot of the energy taking off of the ball, and it'll slow down but it'll sort of bend round the hole, the protons like the hole there and the electrons like the golf ball. And from that, you get X-ray photons lit off. Take that into just a flare process, and all you've got is just tons of electrons and tons of protons. And they're just, every interaction between them is letting go of an extra emission. That's all you need to know to generate. So the starting conditions of those, of the electrons and the protons, that's all you need to know, and you can generate what you should see from your telescope and what temperature that should be. So that's really useful. Another useful point is that I've got straight to the observer there, which might seem a little bit redundant, but one of the good things about X-rays and also EUV to an extent as well is that they're traveling through emission that is optically thin. So that means just to make that clearer is that pretty much once that photon's emitted, it doesn't interact with anything else. It comes straight and you're the first thing that it interacts with. So you're really making measurements of the flare, whatever it is, as it happened, because it can't interact with anything else. When it comes to like radio or anything like that, there's a lot of scattering. It's difficult to pin down where it's come from, and that's a whole pain in itself. So there's so that's how well understood X-ray stuff's understood. But there's tons of solar events. I just thought it was worthwhile looking into them a little bit. So you've got a lot of magnetic loops. If you saw some of those images before, you'll have seen the sun's absolutely lacing them, especially in the corona. All of these loops you can only see, it's like the filings around the bar magnet that you might have done in school, where all this plasma material's filling up these bits in the magnetic field, and you get loops. Sunspots, again, well, rather than in the corona, these are actually in the photosphere. You've got observations going back hundreds of years of scientists recording sunspot locations. There's also an area of research of scientists now that are digitizing them and trying to get new results out of those. So you can see those with well, don't look at the sun with the naked eye, but you could see them. It's in the optical range. You get coronal mass ejections. Now those are sort of can be coupled to flares. As a flare happens, it might spew off a lot of material. And you also get prominences, and prominences even are really weird. They're also called filaments. They're just sort of like this big. They don't really do much for a long time. They're just these big suspended bits of mass, big loops that go across the sun. And they might add to the mass, this stuff that's chucked off in a coronal mass ejection, but you might see them if you look at the sun as well. So I thought I'll put in some movies, some more interesting ones. So there you see that coronal mass ejection actually firing off. In the top middle there, you've got a flare. So this one doesn't seem to have produced a coronal mass ejection. So they're not always linked, but they can be quite common together. This one, I can never resist putting this in a talk. If I can put it in, is coronal rain. If you've never seen that before, it's really, really weird. So you'll see it starting now, where you'll just get these blobs. So a flare's happened, some sort of heating event's happened, and in the loop, what will happen is that the material up there is so hot that the telescope can't see it, and it'll cool down, and it'll cool down into the temperature that the telescope can see. But as it's cooling down, it's also falling down the loops. So you get this really lovely waterfall, like sort of coronal rain stuff happening. And another thing as well, it's something that it was never something that crossed my mind when I was starting off doing like solar research, but you get things that get in the road of your telescope, and sometimes they can be useful and also really interesting to look. So you get the moon gets in the road, and you also get to see loads of transits as well from a lot of these telescopes. So if I'm going to focus more into flares, I can't really do a flare talk without mentioning the Carrington Event. If anybody has ever been to a talk that's talking about flares, you'll have heard of the Carrington Event. Really should be the Carrington-Hodgson event, because Richard Carrington and Richard Hodgson both saw it and reported it independently, but Carrington gets the credit. And this is Carrington's drawing of the sunspot that he saw in 1859. And what he did was he was observing the sun, making sunspot logs, and he noticed a bright flash, and then about maybe 24 hours, 48 hours later, there was a lot of auroral activity, pretty much a massive geomagnetic storm now, where it was that extreme. The aurorae was quite close to the equator. Electrical equipment was reacting to it, so there were reports of telegraph wires and telegraph lines that would still be able to be powered even if you turned them off, and people would get electric shocks from their electrical equipment because of the massive event that this Carrington event was related to. And that sort of kicked off this thing about that there might be something on the sun that we can't necessarily see in the optics with our, in the same wavelengths as our eye, that that there's something going on here. For some scale, we use something called the GOES class. So I've already talked about the GOES satellite, and I'll get onto that soon. But effectively, this is an X3 class flare, which an X class flare is the highest classification that you can get. The Carrington event was about 10 times higher than that, or more than 10 times higher than that, it's estimated at least. So you can see in the telescope here, or the atmospheric imaging assembly, that even an X3 flare is just saturating the detector. And that's only an X3 compared to the Carrington event. If an event like that happened today and it was facing the Earth, it would be quite devastating. Oh, I've put a link into the page. Perfect, right. So I mentioned the GOES scale. This is what the GOES scale on the right would look like if you sort of just were looking at the graphs online. And you can see where flares have happened. Sometimes they're easy to pick out, like these big spikes over here on the right. That's going up to maybe an M class flare and an X class flare there, with the scale running down the side. I don't know why they've said X, M, and then started trying to jump into the alphabet. It doesn't make sense to me, but that's the sort of scale that we've been landed with. And effectively on the left, what I've got is the general cartoon of what's actually going on in a flare. So this starts off as just an ordinary magnetic loop. And what happens is you've got this material. It could be like that big prominence that I showed earlier that comes up and might go underneath that loop. And what will happen is it will start to rise and the loop will start to rise with it. And as it rises, if you imagine it like an elastic band, if you just leave it quite relaxed, it'll be like an oval. As you start to stretch it, the sides will start to come closer and closer together. You start to stretch it more and more. An elastic band would snap. But what happens in a flare is that we believe that as it gets stretched out that much, that effectively, rather than the magnetic field going from the bottom all the way up to the top, stretching right above this big bit of mass, this loop that's going through it, all the way back down, pretty much to get that close in at the middle that they'll reconnect, so to speak. And so you'll start getting a loop forming at the top, and then, or a circle, like a blob, a plasma blob at the top, and then you'll get loops, hot loops forming at the bottom, where all these particles are getting accelerated and slammed into the solar atmosphere. And so just, I wouldn't suggest looking at this diagram for too long. It's sort of weirdly hypnotic, and it hurts your eyes if you do it for too long. But effectively, this is the idea of what's happening in this bit with the red and blue arrows, is that these magnetic field lines are coming in closer and closer, and you can see that you're getting some loops forming at the bottom, because those would be connected to the photosphere, and then you've got that plasma blob stuff with matter in it rising up off the top, and that happens really quickly, and it produces a lot of energy. So the GOES scale we use, that's that X, M, C, and B, and you'll notice the A's left off here, maybe, so A's somewhere down at the bottom of this slide. And the reason why I wasn't bothered that A wasn't on there was because flares go over a massive, massive scale. So as we saw, the Carrington event was much higher than an X-class flare. So if I kept the same graph, it would be maybe somewhere up here above the word scales. And I've put this X-class flare here, and just it's an X7, that one. So it's still, again, an X7. It's easily saturating the detector. And this is an event that's actually from an event that I had studied. And we found, because NuStar's fantastic at what it does, it's very, very sensitive. It's not actually a solar telescope. So it's made to observe things much further away. So it needs to be sensitive like that. And we found this to be about 1,000th of an A-class flare. So that would be pretty much a whole other group of these, of this graph below the bottom there. and that's how small that is. So that's the sort of scale that we're talking. And I've put a sort of a line in that top graph to show you just even the physical size, the scale of that. So they go over many, many scales, many energies. In the weird ones, the weaker ones happen far more frequently. So the reason why those are of interest, perhaps more than the brighter ones, even though that the brighter ones up there look a bit cooler, is that even though that the one in the bottom there, that the 1000th of an A class is a lot weaker, they might occur more often, and so the overall output of the weaker events is actually greater than the infrequent output of the larger events, if that makes sense. So when it comes to the coronal heating and wondering where is all this energy coming from, it's already sort of settled that there's not enough big events to account for it. So perhaps it's in the weir events. So there's a lot of stuff that you can really go into in solar flares. There's pretty much regions of research in every single one of these sections of the graph in the right here and in the left. But effectively what you'll see at Earth, if it's associated with a coronal mass ejection, is it's sort of layered. You'll see a lot of the stuff from the flare really early on in the CME, because it's the heavier particles that are coming from the coronal mass ejection. It'll get there a few days later. And it's a CME when we're at Earth that really causes a lot of damage. When it's coming to what the flare's doing, if you're looking across, and you can see here that if we're looking at hard X-rays, so hard X-rays are just the higher energy ones. We make a distinction between hard and soft X-rays, just the higher energy ones and the lower energy ones. But you can see that they peak here in the impulsive phase, so that's when the flare's happening and everything's kicking off. And then down here with the EUV and soft X-rays, that's more after things have sort of kicked off and everything's then getting heated. So all this material's coming back up into the loops, and that's where we start sort of see those materials. So again, X-rays sort of get a foot in both of those camps. EUV and all of these other ones have only sort of got one side of it. So again, just the importance of X-rays. If you were wanting to observe ones, or if you're wanting to be on the lookout for any flares, when would you look at them? Well, the sun goes through an 11-year cycle of activity. We're currently just heading into a maximum. So it was great for New Star looking at smaller events, maybe about a year ago, but now not so much. But you can see here that, you know, it's fairly reliable, and we've got data going back to the 1600s. Where people have taken those sunspot numbers, the more sunspots the sun has, the more active it's going to be. So that was where. This is another pattern that you can see in the sun. So at the start of a cycle, you'll get them actually appearing quite far away from the equator. And as we go through this 11-year cycle, they migrate towards the equator. So if you plot this out, so this is just the year along the bottom here, and just the latitude up on the y-axis here, and you'll see that you get these nice, this is a butterfly diagram it's called. So effectively you can see that they start off really far away from the equator, and as the solar cycle goes on, they get closer and closer and closer, and then the next solar cycle starts, and then they start up further away again. Why that happens is again another massive area of research, and there's some ideas but nothing conclusive yet. So just in the last 5 minutes or so, I thought I would go in and actually show you what maybe analysing the flare data is like. So I've gone through, you know, the types of telescopes that we can use, the types of events that we can look at, and some information on flares to how to interpret them. But how would you actually go about doing this? And I'll say leave links at the end, but all of this data is open source. Anybody, as long as you've got a computer, put in some time to learn a little bit of coding, you could all absolutely recreate all of it, if not the vast majority of it. So if you want to pick an event, or you've maybe scheduled time and you've got an observation from a telescope, then you might know where to look, but effectively you might start making images and movies to get a little bit of context about what's happening. So this was an observation that from back in September 2018, and it's this big active region here, this big bright thing that New Star will use to point at it and see what we can get from it. And you can see in these different EUV channels, you sort of see different emission, different parts are lighting up. So we investigate that. as we go through the analysis. So once we've sort of got overview stuff, the next step is really have a more in-depth look. Still sticking to movies and images, you still want a sort of comprehensive overview of, you don't want to miss something really interesting that's actually, you know, going on, but because you've had it fixated in your mind that you know what you're going to look at. And so in the top here, you've got this extreme ultraviolet emission. New star observed on the 9th and the 10th, so that I've just got images here, and you can see the really rubbish in comparison resolution that we've got in X-rays compared to the UV, but it still absolutely shows up here. So this is what this active region looks like in X-rays on both days. And so once we've got that and we know what we're actually looking at, we can then go and make time profiles, light curves. Let's actually see if there's anything that maybe you can't see with the naked eye, just sort of looking at movies. You can get tricked by the frame rate that you decide to make the movies at. You know, that's a common thing. So it's something to always be aware of. So you can make these light curves, and there's a lot of information on there, but effectively all I'm doing is in that white box, I'm just adding up all the light for every frame that the telescope's taken, and I build up these curves on the top and in the middle here. And so these are like the EUV ones, particularly in the top row. This middle one's calculated slightly differently. So I'll not really go into much detail unless someone's interested. But in the top here, you can see that there doesn't look to be that much really happening. You know, it goes up and down a little bit, but there's nothing that much interesting. If you then look down here at what we can see in X-rays, there's tons of stuff happening. Quite easily you can label, or I've managed to label there 10 events, and there's like some really big obvious ones like 3 and 10 that just about show up in this green curve at the top, but other ones like 4 there, that is tiny and you've got no chance of seeing it. So these sort of flares are the really small end of things, it's really easy to see in X-rays, and so you really need X-rays there. Just honing in on one, once you've got that sort of overview, you would maybe hone in. I've honed in on all of them and done research on all of them, but just to pick an example of all the different types of things. I don't know why that video is doing that, that's not great. But effectively, when it's not doing that, you'll be able to see these are just the 2 different versions of that EUV. And you can see that in this one, you don't really see much happening at all. And then in this bottom one, you can actually maybe convince yourself, you know, what the flares are actually doing. Making a little bit closer, more of a detailed view on the light curve here, splitting all that up. So this is what this micro flare or small flare is doing. And then you can take emission from different telescopes and start overlaying them on each other just to see how they match up. Do they actually brighten in the same place and at the same time? And from the X-ray stuff as well, we can then get a spectrum. So that's what a spectrum would generally look like for us, where it's the energy or the wavelength, effectively, like the color of photon along the bottom, and then how bright it is up and down. And from this red curve here that we can fit onto, and remember that red curve only comes from just making a statement about what the electrons and protons are doing at the time. You can then say that what this flare is actually doing is heating stuff up to about 7 million Kelvin or 7 million degrees, which the corona is about 1 million degrees, photosphere is about 6,000. So that's maybe where a lot of the hot material is coming from. It's just a question of how much is that contributing to. And just this last slide here, I thought I've said a lot about, you can step up through the atmosphere, and the videos are being weird in a different way, which is weird because they're the exact same videos, right? But anyway, again, this is the corona, really low down corona. Again, you can't really see much. This is pretty much as high as what you're going to get, and you can see a lot of material being heated. But what we've done here is looked at what's happening on the photosphere, so that lowest level, or the surface, if you like, of the sun, and we can get that through a magnetogram, which is what the magnetic field's doing here. But this is, we're seeing stuff on the surface of the sun, and you can see that as this hotter stuff is happening, that it's pretty much bridging a gap between this big white section and this big black section. And then there's a foot point that's going down to this black and white section down here. if you can convince yourself that that's there, and if when we analyse that further, we actually see, and it might be easier to see up in this image where you've got this little white, so that just means that they're different polarities, so of the magnetic field, and effectively as that flare's kicking off, as it's being triggered, there's some interesting activity going on down here. So you've got some activity in the highest point in the sun's atmosphere, and something down in the lowest, and then it's murder to get anything out of some of the layers in between. So it can be really difficult to sort of piece all of this together and get an idea, a coherent idea about what's actually going on. So that's an idea about just some general flare research. And so I've just got this summary here about the main things that I've talked about. That there's tons of different ways that you can observe the sun, different things that you can focus on with your spectra, imaging, light curves, things like that. And there's also different telescopes designs that you can use, and they've all got their uses, and sometimes you can only use certain types. Flares occur over a huge scale, so it's not always the big, really cool, flashy ones that you might want to look at. You might want to look down at the weaker ones. And X-rays and EUV, they're really essential if you want to study these. And that's why we need the telescopes up in space. That's sort of the justification for spending a lot of that money on a telescope that you can't replace, you can't fix, but we need them up there. And I'll just leave this here. I've got 3 links, and you can either scan them, you can go and follow those links at the bottom if you like. Effectively, the one in the far right is an overview of all the New Star telescope solar observations that the team that I collaborate with, what we've done. There's links to all the papers there that we've published as well, so if you're interested in reading any of them, and going and seeing what else we've observed on the sun with New Star. In the middle here, I've got one that's HelioViewer. I don't know if anyone knows of that or have ever heard of that. That's pretty much, you can get really up-to-date optical UV X-ray images of the sun. You can even get those magnetograms to find out what the magnetic field's doing on the surface, and you can download them as images. You can make movies of them as well, and they're very recent, so if you wanted to go and see what the sun was doing 10 minutes ago, you could go in and do that. And similarly, Solar Monitor, over the link for that over on the far right, it's very similar as well. It's maybe got some other instruments like the GOES light curves, you would maybe get them there as well. So in just that little point down at the bottom that I'll end on, as I alluded to earlier, all of this data, at least that I've used in this presentation, it is all open source. Every bit of code that I've written to do this has been done in Python. If I'm sure that some of you might have used in the past the Python coding language. And there's tons of examples out there, so even if you didn't really know much about that, you could just copy and paste some examples to get some amazing images out of this, because it's all publicly available. But thank you very much for having me and listening, and I'll take any questions. And yeah.
Kristopher, thank you so much. That is just a superb talk, and beautifully guided through. That is really excellent. One exciting field, though. I had no idea half of this stuff was carrying on. It's fantastic. Yeah. How we do this? Have you questions coming in, David? Or
yeah, there's one from Scully on YouTube, and he's asking, which I think you kind of covered a little bit, which is what exactly is the difference between magnetic loops and prominences? Although I think there was a diagram that kind of showed a little bit about how they interact. So maybe just explain that a little bit more.
No, absolutely. I'll go back and I'll find that. So this is actually something that it's always really confusing. There's tons of things in the sun, and that's an excellent question. First of all, there's tons of things in the sun that, just like the GOES class, saying we're sort of just stuck with these letters. There's a lot of things that have been observed in one wavelength. They've called it something, and then that field of study goes ahead and does tons of things, and then you look at it in a different wavelength that looks slightly different, so they call it something else, and it takes years for them to actually meet up and go, wait, these are the same thing. So when it comes to prominences, I've got a friend, one of the other PhD students at Glasgow, who he researches them, and I'll wind them up and just say it's pretty much just a big fancy coronal loop. It can be a little bit more complicated than that, because coronal loops, if you look up at the top here, you'll see they're quite nice and well defined. You know, they're all quite, you can follow one line, more or less, especially in that fine scale structure. When you look at the prominence though, it's a little bit more jaggy as it's going along. And so what the idea here is that you only get material in bits are flowing in bits where the magnetic field's null, really. So when it's zero, so that's why you get a lot in when a flare happens and those magnetic lines meet each other, it creates a null point and there's tons of acceleration. And so what happens is these form across our own polarity inversion lines are called. So that's along lines where you've got maybe a lot of negative polarity in the magnetic field over here and a lot of positive here. At some point it's going to go to zero. You know, there's a 0 point in there, and that's where all of this material sort of fills up. So that can be supported by loads of loops that you can't see here. So if you look at maybe, if you just pick some of these loops and sort of coloured in over the top of them. So these loops are like supporting all that material where it's all sort of flowed into. So as it's a whole area of study as well. It's quite complicated to know what you're actually looking at. And it's effectively down to what the magnetic field's doing, and also the temperature of them as well. So the magnetic loops actually are usually a little bit hotter, whereas the prominences are that material that's like chromospheric material. So it's down at maybe the 5 to 10,000 degrees. So that's a little bit cooler as well. So that's the difference between them as far as I understand it. I hope that's answered the question somewhat.
Right, yeah. We'll get any more feedback if it's not answered it. Anybody on Zoom got any questions?
In the corona, with these phenomenally high temperatures, I mean, it's pretty thin atmosphere. So I've never really quite cottoned on to how it can be as hot when there's very little material there. How does that work?
That's a very, very good question. You would fit in at many conferences if you would like, please. Like if there's that's in essence what the coronal heating problem is, really. It doesn't make sense at first glance. So, well, and even if you research it a long time, it still might not make that much sense. So yeah, you've got a lot of material. It's very, you're right. It's not got a high density particularly compared. In fact, if I go back, so this line, the dotted line that I showed, that I said I wouldn't bother really paying attention to much. That's the density of what's happening as we're going up through the solar atmosphere. So you can see it's quite high at the photosphere, and then it starts to drop, and then drops, and then it's at an all-time low for the corona. So it is the least dense bit. So you don't have that many particles that are there, but the ones that are there are incredibly hot, flying about, highly ionized. So that's why, for example, that the blue light curve, you might remember the one that I says was calculated slightly differently. Mm-hmm. That's trying to estimate an iron line that's very, very hot, that the actual telescope struggles to see, can't really see by itself. And so it is really confusing. It's quite difficult. But I think that X-rays are pretty much where you need to start looking at, because all of these other telescopes can't really pick up much from there of the hotter material. So yeah, your guess might be as good as mine when it comes to actually knowing why it manages to reach those temperatures. So for instance, two competing ideas that there's still not a conclusion about is, one of them is that flares, that tiny flares, that so really, really small scale flares, as you get smaller, they're more frequent, as I said, and so the net output of the smaller flares is larger than the infrequent brighter flares. Mm-hmm. But we need to see those small scales to see if that's releasing enough energy, enough particles that are then effectively pushing energy out away from the surface into the atmosphere. So that material that's getting heated up, if that's pushing it out, that there's estimates already there. And so if you're looking at these tiny little microflares, you sort of know, well, you know how hot the corona is, so you know how much energy should be getting there. So you can look at the smaller events and say, do we have enough of them? And the value that's usually used is pretty much any study that comes out. It's either slightly above that value or slightly below that value. So the actual value appears to be round about the crucial value that we want to find out. Is it above that or is it below that? Another idea is that waves might carry energy up. So as these flares, and there's tons of other processes. In fact, helioseismology is a very interesting topic. You can map certain things in the other side of the sun that you can't see, just the same way that seismology is used on the Earth to pinpoint where earthquakes and things have happened. It's if there's energy somehow in waves transported up the magnetic field lines themselves. So if you just think about, a rope and you shake it, energy is getting transported up there. If that's how all that energy is somehow getting pushed away from the surface into the atmosphere, that it could be one. It could be either the flares, it could be the waves, it could be both, it could be neither. There's nothing conclusive at the minute.
So still a lot of study to do. I quite like the idea of the waves, because I know there is, like, as well as you said, helioseismology, there's also a lot of interest in sort of audio, you might call it, the effect of like sound waves at very low frequencies in the sun. So I think generally there is going to be a lot of energy carried up by molecular motion and sound, if you like.
Absolutely, and I think that's probably where, like, there's no denying that energy is transported with both of them. So I think that, in my mind, unless something comes out of the blue and that we've never considered before, it's more than likely going to be a combination of both. Because there's tons of things happening on the sun. When a flare happens, you'll maybe have magnetic loops that are right next to it, and when that happens, you can see them jostle about, and all that. So there's tons of things happening on the sun and in the sun that are causing these vibrations. So I mean, they are there. So it's just a case of figuring out to what extent, what role do they actually play.
Can I ask a question?
Yeah, carry on.
Yeah, it's interesting that you mentioned the Carrington event. I mean, that was a huge event, and we didn't have the technology in those days to be destroyed, as it were. How often do you think those events, is there any ideas about how often those events might actually occur?
So yeah, there's some study into that as well, and I think that it's always difficult to do any sort of statistical analysis when that's like a sample size of one. There's studies in trying to look at other stars and see how often do they occur. Do these massive flares happen in other stars? That's difficult because other stars, they can have flares hundreds of times the size of the Carrington event. So like our sun doesn't seem as if that's actually that extreme, but for our solar system it is. There was an event, and if I remember rightly, was it Halloween 2014? Something like that, like in the early 2010s, I suppose. There was a flare that was, maybe, I don't think it was as big as the Carrington event, but it was like sort of that order. It's like 10 times higher than an X quite easily. But it get blasted off the, now let me get this right, the eastern limb on the sun. I had to do that because east is if you're ever looking at anything on the sun, east is the opposite side to as if you were looking at the globe. So east is the left-hand side of the sun and west is the right. But effectively, yeah, it get blasted off there. And that was something that could have done a lot of damage, could have done a lot of damage on satellites. They're pretty much gone. The grid would definitely take a lot of damage there. And the thing is as well, so what, that's maybe 2 in the past 200 years. So maybe it's like a 1 in 100 years sort of deal. It could be more. We don't know what's happening in the backside of the sun as well. SDO's only been up there since 2010, I think.
Yeah, and And from what you're saying, the chances are it wouldn't necessarily be pointed towards Earth anyway.
Exactly, exactly,
Yeah.
and that is a big thing. You can. It also matters as well if it's off to the east, so the left-hand side of the sun. That's better for us than if it's at the right-hand side of the sun, because you get something like it's effectively like as the sun rotates, you get what's called the Parker spiral. So that's firing off emission and the sun's turning. So you get a big spiral that comes out. So you can actually get a bit that's sort of like in the leading edge of the sun that spirals back to us. So if you get a big explosion over there, it can follow those field lines and all that, all those field lines, and it can guide it into us. But it's definitely horrendous if it's facing us directly. Like you said, it might not necessarily face us. Thankfully, that one back, if I'm right, in 2014 wasn't facing us. It was just quite scary to watch and imagine.
How much warning do we have these days about something like that? How many hours would we get?
So when it comes to the flare stuff, like a lot of high energy, some are high energy particles, and all this X-ray emission and that the Earth's going to get bombarded with, satellites need to use that necessarily maybe to shut down. It might be too much for them, so they want to shut down. You don't get any warning really at all. Those are traveling at the speed of light from the sun. When it comes to CMEs, you might get a day to 3 days warning. Not that long, but it's still something. One of the things that there's a lot of interest in now is effectively flare forecasting. So we don't know when these types of events are going to happen, and so the Met Office has got it's really cool to go and see. Actually, they've got like a section in their big massive operations room, and they've got a solar monitor station, and they've got all these screens and all these channels that, again, like I said, you can go and have a look at yourself and download yourself. They're watching them constantly on the phone to other international bodies, monitoring the sun, and they're looking to try and get our research is getting done to try and maybe get, I think they're aiming for something like 5 days warning or something like that. But at the minute you're getting, I mean, you're not even getting like 10 minutes warning or an hour warning. I think the last thing that I heard was the best forecasting that's still getting done is a handful of scientists that look at the sun as a job, like in the Met Office. And for some reason, they've got a knack of going, I'm going to watch that region for a little bit longer because it looks as if something's going to happen. But to try and there's been a lot of money piled in, some lasting years, and it was a lot of money in the millions. It was then ultimately found nothing at the end of it because they had all of these different things that they were monitoring, and they were trying to find some sort of pattern, and they couldn't find any at all. So it is very difficult. And there's also another weird thing where all of these models that people do to try and predict what's going to happen, what should we look out for that might say, this active region in the next 24 hours is going to do something. There's a really weird thing that if you take all the different types of models, so all of the predictions, and then take the average, it works out better than any individual model. Which is really weird. So it reminds me of that thing where, like, if you ever play that game at like a fair or something like that, and it's guess the number of marbles in a jar.
Yeah.
And any one person's not going to get it, but actually if you average everybody's guess, you get very close. It's somehow with really complicated models.
Yeah, that's something they can't explain. That's a mysterious thing. Yeah, I've seen that on the TV. It's very mysterious. Yeah. So it sounds like even if they were forecasting something, they wouldn't actually do anything very drastic because they just wouldn't know whether it would work anyway, like switching off all the generators, which would be have dire consequences for the country anyway. So it doesn't sound like there's very much we can do.
Yeah. Well, I think that there's, but when it comes to generators, when I was in the Met Office, it was actually really surprising what their plan was for it. So I think it can depend on what country you're in and how their grid's structured. But apparently for the UK, their plan is if you get an event that's like, you've sort of got any warning at all that a big event's happening or about to happen, they actually want to turn as many things on as they can. And it's to spread the load. If they spread the load, then it means that they don't have to shut anything down, and the system as a whole takes less damage. Because that was one thing that I just assumed, perhaps similar to yourself, where I was thinking, yeah, you want to sort of like just shut down all the systems that you really need. But yeah, their plan was to start bringing things back online onto the grid to help spread that load, which I thought was quite an interesting tactic. And I'm assuming that's the best way to deal with something like that, just with how our grid's structured.
So you all to switch your kettles on.
Drink lots.
Yeah, keep notifications on from the Met Office just in case that comes up.
Guess we all hope that the guy that's good at reading the monitors isn't on his holidays that week either. So,
Yeah, I was just thinking on that, on the forecasting, that possibly that's a sort of something that AI deep learning could build up enough models, like neural nets, that by observing these regions and what happens to them over time, you could get an AI model to predict more accurately. Building up experience. Yeah, so it's possible.
That's a very interesting area of research. There's a couple of guys who are phenomenal at it at Glasgow, and one of them is actually left the field now. But yeah, pretty much that seems to be it. They seem to be amazing at picking out these patterns that no one's got a hope of finding. But it's hard to argue with the results, because they are reliable and they're better than just chance. The only difficult thing is it's a black box. You put stuff in and you get something out, and as far as I understand it from them, there's not a reliable way to actually understand what it's done in the process.
Oh yeah, that is the problem with like deep learning systems, that they build their own model, but the model is so complex that there's no way a human can understand what it's doing. But then with the guys at the Met Office who seem to have this knack, could they explain what they're doing? Is it just something they've developed?
Yeah, I don't get. I was sort of taken aback when I had heard that. I was going like, I was at I can't remember what conference I was at, but yeah, they were just saying like, out of all this money that's been spent, all the time and effort that's put in, it's still somebody will be like, I bet you that region's going to do something soon, and it does. And I just think it's bizarre.
Mm.
What do they know? What is going through their mind when they look at that?
So how long? I mean, high energy solar physics sounds a fairly new science in terms of the level that you're able to work at now. I mean, how old is that?
That's a good question. So I think there's always been high energy physics, high energy solar physics. I'm trying to think back. The first observations were done on hot air balloon, or by balloon measurements. Now that I don't know whether I'm making up the hot air balloon, it might be, but then I think it's like maybe back in like from the 60s, 70s sort of time. But again, you would only really get these sort of like light curves, the time profiles. The imaging that you would get from the high energy stuff that we're really talking about now with like New Star and that. RESI, I think, went up at about the end of the 90s, maybe like 2000 or 2001, round about then. It's been since decommissioned. It lasted. It's typical of a lot of these telescopes. They're built very, very well, so they outlast their mission time. But it was back in 2015, I think, that it was then finally it was decommissioned. There was too many things that just weren't working on it anymore. So that sort of propelled the field a lot, because then you could start getting images from it. You could still get your time profiles from flares, and you were starting to get these actually being able to do spectroscopy. You get the spectrum out of it to then start saying, like this stuff must have come from this temperature of material. And in fact, at that point, I think up until maybe 2007, 2008, a lot of these, like the models, the computer models, because the way that you fit these is effectively like you sort of make a model with that temperature, and it tells you what it should look like, and you compare that to what you see, and you'll then tweak the temperature and get a new model, and you'll either throw away the old one or keep it and sort of keep tweaking it, and you'll do that thousands of times. The computer will do that thousands of times to find the best match. The code itself, like the program itself, wouldn't run fast enough to do it to the depth that we can do this analysis now as well. So there's a lot of facets to this. But yeah, it's probably been since RESI went up, that's probably like the modern sort of high energy X-ray imaging sort of stuff that we've got back in maybe around about 2000.
That's quite amazing, isn't it? The amount of work, yeah.
I was going to ask about the telescopes. Do you have to book time on them the same as you would for like time on the Hubble and things like that?
Yep. So I think we've not long handed in another proposal. So particularly with new stars, so with like the SDO, which is our SDO AIA, so it's a Solar Dynamic Observatory Atmospheric Imaging Assembly. That's what these 4 images are from in the right, and I can't stress this enough. It's open source. You know, you could go and look these up. You can download them, the actual data files, and play about with them and do really cool things with them. You don't have to book time in them. Those are constantly observing the sun. Sometimes as you saw in one of the videos, the moon might get in the road, and the instrument doesn't know what to do. Then it starts like throwing the sun about the place because it can't get the coordinates right. But when it comes to using instruments like NuSTAR that I use, or my collaborators use, you have to then put in a proposal. So it's an astrophysical telescope. It has its issues when looking at the sun. It's a wee bit of a pain because the sun's by far brighter than anything else that it's looking at. But yeah, you have to put in a proposal, describe, so it's maybe 3-4 pages, and you're just sort of outlining your science goals and your expected return, the importance of the science. We seem to do reasonably well because it's an astrophysical telescope and we're wanting to do it with something really different like the sun. No other team really uses it. I think they've had one other proposal in to look at the sun. Everything else is an astrophysical source. So yeah, you absolutely have to go in, you book time, and it's like a lot of these telescopes you have to book time in kiloseconds and thousands of seconds, which I think's weird. So it's like you're still putting in for thousands of kiloseconds, but that works out to be you get some nice hour long slots to look at the sun, because the Earth gets in the road with NuSTAR because of the orbit that it's on. So that's why shouldn't have put all these animations in. But yeah, you have to book time on that because it's just not a solar dedicated telescope pretty much. So there's NuSTAR's eclipse, so the moon gets in the road there. There's a lot of liaison with the people that we're actually trying to book the time with, because you've got this bit when the Earth gets in the road, but you'll also notice there's gaps in the red data like that aren't in that eclipse bit. So you can see one in here and in here. There's the SAA. I don't know if you've heard of that before. So it's a South Atlantic anomaly. It's a bit where I think it's the Van Allen belt sort of dip a little bit lower than where they normally are. And when the telescope goes in there, they have to shut it down because the count rates go through the roof if they don't. So we also communicate there with saying, like, is there any chance that in the time that we've requested and been awarded, can we have any orbits that won't have big gaps in it? So there's a lot of back and forth with them, which isn't necessarily the bit that's sort of the open source way, like that somebody who's sort of interested in this sort of stuff could maybe do. But all the data that we've collected so far, that's all publicly available. So if an observation's already occurred, that's up on the NASA's website that you can go and download and play about with as well. That's more complicated to get working right because you need to use NASA's software, and NASA, I've learned, aren't very good at making their software. Whether it's a coding language or something else, but you have to sort of get that working. But yeah, all of that's available if it's already been observed, if that makes sense.
Yeah, I can understand. Do all the I presume that some of the telescopes, because I know there's quite a few X-ray telescopes up there, I presume some of them you probably don't want to point at the sun because of the delicacy of the instruments and such. But you know,
yeah, absolutely. I know that there was a panic. So the first observation with the new star in the sun was back in 2014. So that was a wee while before I started my PhD. But I know that there was panic when they pointed at the sun, and I think there was an X-class flare that happened while they were looking at the sun. And the papers on that link, so the summary that you can see, you can go and look at that. The first one where it was sort of just like, look, we've managed to point it at the sun and new star didn't break, because we've just got images that are just completely flushed out, like, because new star is very sensitive, so it's just, you can't get anything useful from it apart from saying it's observed something that's brighter, that it's pretty much observed the brightest thing that we'll ever observe, and it's still working. So that means that we should be allowed to point it at it again later.
That's yeah. Luckily, it survived it. I noticed there was one launched because I'm quite interested in spaceflight and spacecraft. There was one launched in December. Was it an NASA Italian new X-ray telescope?
Perhaps was it a solar one? Or was it just a?
No, it was IXPE.
IXPE? No, I've not. Right, I might read up that. I've not heard of it.
It's probably not
that myself.
Yeah, they launched from SpaceX. Did one of the Falcon 9 launches, and yeah, I've got a semi-professional interest in it, you might say.
Yeah, it's difficult not to when you start looking into this sort of stuff. I think it's you know, it's really interesting.
Yeah, so you might get some time on that once they get it commissioned as well.
Fingers crossed.
Yeah, I think Ken on YouTube saying he's thinking with the increasing solar activity that he might invest in an H-alpha telescope. So certainly
beautiful images.
Some interest.
Yeah, you get beautiful images off of an H-alpha filter. It's just, tons of science that you can do with it as well. That's one of the few lines that it actually interacts with multiple layers of the atmosphere. So you can tell a lot from an H-alpha image, because it's sort of like different parts of the emission line is formed at different parts of the atmosphere. So if you just isolate them, you can sort of step up through the atmosphere as well. It's quite, but yeah.
Cool. All right, there's nothing else coming in on YouTube at the moment.
Kristopher, thank you so much. I mean, that is just a fascinating area and a super talk about it as well. So I'm sorry we didn't all get to the mills and actually meet you there, but certainly wish you the very best finishing off your thesis. And I hope you get a really super, postdoc post and carry this on a bit further. You're not going to be short of questions to ask us, for sure.
Oh, I know. I think that there's always more to ask. But no, thank you very much for having me along and coming listen. And I'm glad that you enjoyed the talk. Thank you very much.
Very much, really very much. All the very best.